Hello friends, I am Professor K.S. Tanpure from Zeal College of Engineering. Today I am going to discuss about yet another topic from physics, that is oscillation. Now under this topic we are going to discuss about linear simple harmonic motion, angular simple harmonic motion. We are going to take some examples which comes under linear simple harmonic motion, some examples under angular simple harmonic motion, and the last part, that is a simple pendulum performs simple harmonic motion. So this is what our video will include. Let us start with simple harmonic motion. Now what is simple harmonic motion? Any to and fro motion of any particle from its mean position is nothing but a simple harmonic motion. Now what is linear simple harmonic motion? When a particle moves to and fro from its mean position in linear direction, may it be in horizontal or vertical direction. So if the displacement is in linear direction, then it is called as linear simple harmonic motion. If whatever the displacement of that particle from its mean position is having certain angle, or we can say angular displacement, then it is called as angular simple harmonic motion. Now let us understand this linear simple harmonic motion using one example. Now the example is given as mass attached to a spring. So I am considering a mass which is considered as an object. It is attached using this particular spring through a support. Initially the mass is at mean position, MP stands for mean position, and whatever this line I have drawn is the CG of that particular mass. Now once if I am applying some amount of force in downward direction, if I give this system a downward pull, then we may say the spring is stretched from its mean position. So I can say the mass has displaced some x displacement from the mean position, which is considered as positive displacement. Now the mass which has been stretched in downward direction gets compressed in upward direction, and we call it as a negative displacement. So the mass moves to and fro from the mean position in linear direction, that is in vertical direction. So this is an example of linear simple harmonic motion. Now what happens in this particular case? When the mass is stretched downwards or it is pulled downwards, then the spring gets stretched. What is K? K is spring constant or force constant. Then what is X? X is the displacement in downward direction. X is the displacement in upward direction, but it is in negative sign. Now once the mass goes down, the acceleration of that particular particle is in downward direction. There is always a restoring force of that particular system which brings back the position of this mass to the mean position. So what is the restoring force? The restoring force is F is equals to minus Kx. K is the spring constant, X is the displacement. Now there is a minus sign which is shown in this mathematical formula. F is equals to minus Kx. This minus sign comes as restoring force acts towards the mean position. As the mass moves down, it is accelerating in downward direction. There is always an opposing force in upward direction, and that's magnitude is equal to multiplication of spring force into its displacement. So it is always directed towards the mean position. So this minus sign comes due to that. And second condition is restoring force, or the magnitude of restoring force is directly proportional to the displacement. So these are very important two conditions as far as any body which undergoes simple harmonic motion. Now according to Newton's law of motion, we have F is equals to ma. So that is acceleration is equals to force per unit mass. We are using F is equals to ma. Let this equation be B. We are putting this equation B in equation A. What you will find is ma is equals to minus kx. So acceleration can be found out using this particular expression. A is equals to minus k by m into x. That is if we replace k by m with omega square, that is your frequency, then A is equals to minus omega square x. Now, if I want to find out this frequency in terms of hertz, then I have to use this formula. F is equals to 1 upon t. Now, what is t? T is the time period. 1 upon t is equals to omega upon 2 pi. So, finally, the equation of this particular system which undergoes linear simple harmonic motion has formula F is equals to 1 upon 2 pi under root k by m. That means, for a linear simple harmonic motion, restoring force always acts towards the mean position, and the magnitude of restoring force is directly proportional to the displacement. Now, next type of simple harmonic motion is angular simple harmonic motion. Get it understood using an example. Now, in this particular example, I am having a disc which is connected through a shaft which is having certain mass, and it is suspended from a fixed support. Kt is the torsional stiffness, L is the length of the shaft, and disc is having certain radius. Now, this type of angular simple harmonic motion is analogous to linear simple harmonic motion. Only certain factors gets changed. Instead of spring constant, we have torsional stiffness. Instead of mass, we have to take inertia of the body. Instead of linear displacement, we are going to take angular displacement. Other things remains same as that of linear simple harmonic motion. Get it understood using this example. Now, I am having this disc, I am having this shaft, and I am having this support, all together forms a system. Now, I am going to provide an angular twist to this particular disc. Once I provide an angular twist to this particular disc in anti-clockwise direction, the accelerating torque is going to act on this particular disc. That means, initially, if my particle is at this position P1, it will try to attain another position P1 dash in anti-clockwise direction. That means, I am providing an anti-clockwise twist to this particular system. Now, once I am applying certain amount of force, or you may say torque, to any system, there will be always a restoring force acting in opposite direction to that of accelerating torque or force in order to maintain the mean position of that particular particle. That is what we have learned in linear simple harmonic motion. So, the particle which has displaced from P1 to P1 dash will always try to come to its mean position. So, there is always a restoring torque acting on that particular particle. Now, what is the magnitude of that restoring torque? It is nothing but multiplication of torsional stiffness into the displacement through which it has displaced, that is angle theta, or we can say angular displacement. So, the restoring force is Kt into theta. If I write in mathematical formula, then torque will be equal to minus Kt into theta. Again, minus is nothing but restoring torque which is directed towards the mean position. So, there comes a minus sign, and magnitude of restoring torque is directly proportional to the angular displacement. So, any body which uses these two conditions, that means that body or that object or that system performs simple harmonic motion. This disc is having angular displacement, so this is an example of angular simple harmonic motion. Let us derive the frequency of such a system. So, torque is equals to minus Kt into theta, let this equation be A. Torque is equals to I into A, that let it equation be B. If we compare these two equations, that is A and B, we are going to get acceleration is equals to minus Kt upon I into theta. Let this equation be C. Now, according to Newton's law, we have A is equals to minus omega square x, which we have discussed in linear simple harmonic motion. A is equals to minus omega square x. As this is an angular simple harmonic motion, x is replaced by theta, what we have seen here. X is being replaced by theta because this is linear displacement and this is angular displacement. So, A is equals to minus omega square into theta, let this equation be D. On comparing C and D, what you will get, omega square is equals to kT upon I. That is, omega is equals to under root kT upon I. Now, if I want to find out frequency in terms of hertz, then it will be 1 upon time period, or it is equals to 2 pi upon omega, that is equal to 1 upon 2 pi under root kT by I, where kT is torsional stiffness, which is also find out using torque upon angular displacement, or Gj by L. G is modulus of rigidity, J is polar moment of inertia, and L is the length of that particular shaft. In this particular part, we are going to discuss about simple pendulum. We are going to prove whether this simple pendulum performs linear simple harmonic motion. Now, what is simple pendulum? There are two types of pendulums. One is ideal simple pendulum and second is practical simple pendulum. Now, ideal simple pendulum is defined as a heavy mass supported by or suspended by a inextensible, weightless, untwisted type of string from a perfectly rigid support. But if you take an actual examples or practical examples for an inextensible, weightless or untwisted type of string, it is not possible to suspend that particular weight. So, instead of ideal simple pendulum, we are going to consider practical simple pendulum. Now, according to practical simple pendulum, a heavy mass or sphere, which we call it as bob, is suspended by a light inextensible string from a rigid support. So, that is what a practical simple pendulum is and an ideal simple pendulum is. So, in this case, we are considering practical simple pendulum. So, there is a bob which is having certain weight. We are considering it as m into g, that is mass into gravity, which is nothing but weight of that particular bob. Now, A is the mean position of that particular mass, B is the displaced position from its mean position in anticlockwise direction through an angle theta, T is the tension in the string, the point C is the another position of that particular bob. Initially, I am providing certain amount of displacement through an angle theta. So, this mass will move in anticlockwise direction through angle theta. The length of that particular string is small l. The distance L is nothing but the distance between CG of that particular sphere and the suspended part. Now, as the particle moves from this position to B position, the mass acts vertically downwards. So, you will have two components of mass, one will be mg cos of theta and another will be mg sin of theta. Now, from this particular diagram, you can easily find out mg cos of theta is in opposite direction to that of tension. So, tension cancel out the mg cos of theta component of mg. Now, the remaining part is mg sin of theta, which is acting in mean position direction. So, your spring force, or we can say restoring force F, is equals to minus mg sin of theta. Now, for this particular simple practical type of pendulum, theta is very small. For around an angle 6 degrees, theta or sin theta is almost equal to theta, and we are going to consider that condition only. So, sin theta is almost equal to theta. So, putting sin theta is equals to theta, what I will get is F is equals to mg into theta. Now, according to the arc of circle, you have displaced this particle from its mean position in anti-clockwise direction through an angle theta. So, converting this angle into linear displacement. So, according to the arc of circle, x is equals to L into theta. So, x is equals to L into theta. Theta is equals to x upon L. Putting this theta in this particular equation after equating sin theta is equals to theta. So, it becomes F is equals to minus mg upon L into x. In the other way, we can say force or restoring force is directly proportional to minus of the displacement. So it satisfies our linear harmonic motions properties. That is, restoring force is directly proportional to the displacement and restoring force is always in the direction of mean position. So this simple pendulum performs simple harmonic motion can be proved. Now according to the Newton's law of motion, we have F is equals to ma. So we can find out acceleration is equals to force per unit mass, which is equal to mg upon lx upon m. Mm gets cancelled, you will get a is equals to minus g by l into x. This is from Newton's law of motion. So a by x is equals to minus g by l, that is acceleration per unit displacement is equals to negative of acceleration per unit length of that particular string. Also from linear simple harmonic motion, we have already derived this as acceleration is equals to minus omega square into x. A by x is equals to minus omega square. So this is equation number B. So equating or comparing A and B, we get g by L is equals to omega square. That means omega is equals to g by L. Now if I want to find out frequency in terms of hertz, its formula is given by 1 upon time period or omega upon 2 pi. That is equal to 1 upon 2 pi under root g by L. So that means frequency is directly proportional to root of g and it is inversely proportional to root of L. That frequency in terms of hertz.